Hello everyone, welcome to part 2 on this series of using PyReason with machine learning. Today we're going to talk about a temporal scenario that's a little more complex than last time's fraud detection system. PyReason supports temporal reasoning, and this allows us to make use of it in scenarios that evolve over time. So we're going to look at a welding scenario where we have some system that welds components together. This could be done using a robotic arm or some other automated mechanical system. We assume that we have a classifier that's able to examine a weld after it's been performed, and it tells us if it's okay or if there's a gap in the weld. So if it's good or if there's a gap. If there's a gap in the weld, the welding needs to be redone. And to demonstrate this purpose, we rerun this for 3 time steps. But we need to be careful about how many times the model has told us that there is a gap. It's probably not a good idea to continue welding on the same part over and over again. So we need to have a way to conclude that maybe the part is defective after 2 attempts. So this is clearly a temporal problem where multiple actions need to be taken over a course of several time steps. So let's go over the code to see how we can do this with PyReason and to get a better picture. Okay, so very similar to last time's code, we have a very simple linear model that acts as our weld quality checker. This can easily be replaced by an actual PyTorch model, but for now it's just a dummy model. Our class names are good and gap. And if you remember from the previous video, we have several interface options that allow the user to control how the model output gets translated into the logic. So we use the same settings as last time. We have a threshold of 0.5 and we only modify the lower bound. And to recap, what this means is that if the model predicts a probability that is greater than or equal to the threshold, then the lower bound is set to the snap value. So, for example, if there's a probability of 0.6 being a good weld and 0.4 being a gap, then we're going to have a good fact with bounds 1, 1 and a gap fact with bounds 0, 1. And what that means is it's uncertain for gap. We then wrap the model in our PyReason logic integrated classifier class where we specify the model, the class names, and the weld object, the object that we're welding together. So we have 2 very simple rules here. The first rule tells us if a repair has been attempted on a certain weld object. So if there is a gap detected in the weld object, and this fact over here would be given to us by our classifier model, then in the next time step, we know that we're going to try and repair this welded object by welding over it again. So that's why we have this 1 over here, which tells us that in the next time step, we're going to know that we attempted to repair the weld object. We also have a second rule, which tells us if there has been a gap on the weld object and a repair has been attempted on the weld object, then the weld object is defective. And we do this immediately with a time step of 0 because at this point we know that there has been a gap twice on the weld object because there's still a gap and there was also repair attempted, which was triggered from the previous time step. So we flag the weld object as being defective. So that's it for the two rules. So this is where we actually pass our features into the PyTorch model. And these are the features. Right now, they're just a random vector, but the features for the first time step, we pass this into our classifier model. And to be able to specify the time at which this happened, we have these two extra options over here, which are T1 and T2, which allow you to specify when the facts start and when they end. So this weld quality checker, which is a wrapped PyTorch model, will output the logits, the probabilities, and the facts. But the difference these facts have to the facts we saw in the previous video is that they have a time associated to them. So for these facts, we know that they're going to be applicable from time step 0 to time step 0. So for the period of time step 0. And then we do the exact same thing for time step 2. We have a feature vector and we pass this back into our welding classifier, except this time we want this to happen for time step 1. So the facts that get outputted from the classifier are now applicable to time step 1. And we do the exact same thing, but now for time step 2. Uh, And that's how we simulate the first time step, the second time step, and the third time step by adding facts for each period in time. And then what we do is we perform reasoning over these 3 time steps and we print out the trace. So let's go ahead and run this and see what we get. So we run the code and you can see that the probabilities for the first time step are 0.8 for good and 0.16 for bad for a gap. And for time 1, it's 0.7 for good and 0.2 for gap. And for time step 3, you have 0.7 for good and 0.24 for a gap. And what this means is that the weld has been successful over all 3 time steps, and this can be seen from from the trace, where we can see that the weld object classifier has predicted a good weld over all 3 time steps. Now, if we go back to our code and change the seed so that we get different results this time, and run the code again, you can see this time that there was actually a gap detected in the weld at time step 1, but the weld was okay at time step 0 and it was okay at time step 2. So in the trace, what this is going to look like is you have a good weld predicted for time step 0. You have a gap predicted at time step 1. And then because you have this gap at time step 1, in time step 2, you can see that there has been a repair that was attempted. And this was triggered by the repair attempted rule due to this gap. And after the repair was attempted, we can see that the weld object predicted a good weld. So that second attempt actually fixed the weld. And finally, we have one more case. And in this case, we see that the weld was good only for the first time step. For the second and third time steps, the weld was predicted as having a gap. And what this means is that the weld object should be labeled as defective, as we saw in the slides, because we had a first weld, it was okay. We welded a second time, there was a gap, which means that in time step 2, there was a repair that was attempted, and it was not fixed at this point because you see a second gap over here, and that triggered the defective weld object rule, as you can see from the trace over here. So that covers the three cases, and this is how we can use PyReason to work in a temporal setting along with a machine learning model like this weld classifier. I hope this was useful, and links will be provided in the description for the previous video and some resources to PyReason and the documentation. Thank you for watching.